My name is Szymon Matkowski. Today I will talk on methodology for simulating craft movements in low-gravity environments like Mars or the Moon for safe emergency design. A few words about me. I am an executive architect. I design big buildings like from 100,000 square meters above. I'm also a space exploration enthusiast and a member of Nexus Aurora community with many space-related projects ongoing. So I decided to combine those two directions and present some results for you today. Humanity will soon start settling Moon and Mars, constructing fully life-supporting habitats on their surfaces. The importance of habitat safety and reducing the potential loss of life is obvious. Providing safe egress in case of emergency is crucial for people's survival. There are various threats for humans in habitats on other planetary bodies, like fire, rapidly spreading smoke in close volumes, depressurization, environmental control and life support system failures, radiation and solar storms, especially on the Moon, where you have no protective atmosphere, sandstorms on Mars, and ground quakes, also mostly on Mars. So the evacuation process differences. The evacuation process in its basics is similar to Earth. But there are three fundamental differences. First is movement in terms of reduced gravity. And second is that you have a hostile interior and you have no place to escape to. And any threat may lead to base extinction. So main goal of this research is to establish required safe egress time for different habitat sizes, and providing also heightened guidelines for future habitat designers and mission planners. The methodology is based on spatial design guidelines, population typology definition, human behavior, human locomotion, and growth formation in conditions of low gravity. And also simulation software programming techniques. Okay. Before I present elements of methodology, a quick review on researches already done. Of course, evacuation process is a part that is being studied for a long time. SFP experience and publications served as a basis for this study, especially human behavior. Crowd formation and movement studies are progressing, as you know, from the half of the 20th century and being extended by and updated by researchers and institutes. Reduced gravity locomotion of a single human being has also been documented by NASA in parabolic flights, but also in laboratory testing. You may see as an example from New Mexico State University. Also, Milan University is very much progressing in these researches. Also, as a colonization is not yet started, it is no specialized regulatory body except space agencies. Design process is long and costly, with no normative frames established. And requirements, if they are given for missions with a very small amount of people involved in the mission. And I think that this is not suitable for the colonization process. Okay, basic assumptions made to this research is that you already know RECT is less than a viable safe egress time where people get incapacitated. Then bouncing in low gravity is inevitable. People are neither subject to cybernetic nor no genetic modification. So the gait length and the motorics are the same like on Earth. It doesn't mean that it's just a gait length. Human behavior during emergency situations is the same on the Earth. Simulations consider no effect from operation of engineering systems, so everything is down. RSCT goal is designed to 7 to 10 minutes, and then all the occupants are redirected to safety areas. The result model will act only as a benchmark for the future design development. Okay, so methodology elements. To establish the design results, one should analyze people's movements and conditions and speed transitions. Define habitat population with demographical typology. Choose the most significant emerging scenarios. Adapt and document factors and considerations in human behavior and in habitat characteristics. Establish parameters for evacuation process, like delay time, and interpret and finally implement into simulation software. So I will start with the movement speed formula. The movement speed in conditions of changed gravity is based on Froude number of speed transition for particular person. Leg length is assumed to be the same everywhere. So it might be omitted in the formula. Taking that Froude number is the same for different gravities, an occupant movement speed can be obtained. You may see a conversion example for a male in his 30s. So you can see Mars is much slower. The Moon is almost 2 times slower. Okay, sorry. This is example calculation table for Mars conditions. So you can see that there are gender and age ranges, speed on Earth, speed on Mars, and there is a program parameters I use with Pathfinder to program the evacuation. Movement types in different gravitational conditions, environments, the most economical way of movement on Mars is Earth-like, while on the Moon, movement differs significantly and presents a kangaroo hopping. You may observe that in Apollo mission footages. As you may notice, the main formula does not provide information on possible bouncing during the higher speed movements, especially for Moon conditions when transitions to running occurs in very low speeds. Energy-efficient Moon locomotion may consist of different types of movement, like skipping, hopping. This is Moon. And it all depends on cost of transport. You can find it later in my paper. That with Froude number equal to Earth, the transition from walking to running occurs at speed 0.8 meters per second. So therefore, kangaroo style is inevitable by any human being in a non-crowded situation when you have one person per 2 square meters, resulting in speeds comparable to Earth. But it is assumed that for this, also for the purpose of the research, that in crowded spaces, when you have 2 persons per square meter, bouncing will no longer occur or will have a minimal impact on the evacuation time. But people's movement speed will be reduced to the numbers calculated with the formula, which are very, very slow. One of the methods I want to I reflect the bouncing is I provide higher collision response times. Who uses a Pathfinder? They are 1.5 seconds. I use 7. Okay, the next point is habitat population. The population distribution of the habitat impacts RSET significantly. The more differentiated the population is in terms of gender and age, the more accurate the results are. Therefore, 3 population profiles are introduced: dynamic, balanced, and conservative. They were derived basing on the Dunbar number, which stands for cognitive limit of people one can maintain stable connections. This is also a kind of a politics, where you develop the base, you have more and more people, so the political statement changes. So each distribution option reflects also next steps of the colony development. And the small diagram here illustrates the typology. And as you can see, conservative, which is the biggest habitat, is almost reflecting the typical Earth statistical data of progressive countries. So we are developing the colony from a young fit specialist into normally demographical society. Okay. Choosing the right scenario. Humans on the other planetary bodies continuously require habitats for shelter. Therefore, the habitat must be simulated with scenarios that include all main activities: work, leisure, and sleep. Only a combination of results simulated for the worst-case scenarios in those 3 domains can provide the proper design solution. Human behavior factors and considerations. Before starting any simulation, it is crucial to conduct in-depth analysis of planetary habitat. One must be conscious of habitat characteristics, population characteristics, emergency strategies, and be aware of main threats. It is essential that each simulation is properly documented and understood. You may see in the screen, you may see lists based on SFP recommendations, but with I marked orange things that they are characteristic to planetary habitat. Okay. Parameters for evacuation process. Each scenario for any habitat size must consider delay times and pre-evacuation process for detection, alarm recognition, evacuation, and protection period. It is important that one fully understands the habitat composition and life of the colony in the design stage, so to properly define all the parameters for the simulation. As analog to the Earth, you may take scientific stations or mining installations on the northern climates to compare the delay times and work of the facility. But those small Earth-based features do not reflect the colony size. So it is very important to take carefully all the parameters and analyze them. You may see examples of the work on the right. I did for a few competitions already. I made a sum up of them for the habitat of 115 people, 1,000 people, and 10,000 people. Software implementation. Interpreted and prepared data should be programmed into agent-based simulation software, such as Pathfinder, differentiated by the age, gender, and impairment agent types are defined by profiles. Each profile consists of multiple information on movement properties, door choices, travel times. As mentioned before, bouncing, hopping can be also simulated, although it is necessary to underline that none of the software options today provide the bouncing in full scope. The next step is 3D geometry, scene building, and where required by scenario, agent layout is defined. Then, as per scenario and evacuation process parameters, behaviors are established. Finally, the model should be tested and documented with a proper methodology. One of the good sources is, again, SFP Guide to Human Behavior in Fire. Okay. Results implementation. As a result of numeral iterations, recommendations to design are produced. It is crucial to analyze each version of the design, and all the changes to the model should be properly documented and retested. You may see a few example recommendations I give to the planetary habitats during the competitions. The one which is always popping out is the refuge room layout and presence. The refuge room is, I define it as a closed space protected from internal and external conditions with possible access from outside for rescue missions with separate life support system. So possible impact of that methodology is that it, first of all, not maybe between you, but among people who are involved in space exploration, it raises awareness and the necessity of the safety design and evacuation as well. It is essential in habitat design, short-term mission planning, and long development of emergency strategy procedures. It helps to prepare technical guidelines for future projects. It may serve as a guide for drill testing during analog missions on Earth or for astronaut training. It can be also a starting point for the experiments in parabolic flights for the cloud formation, which is not done. And when you exclude the module with low gravity, it could be used in Earth-based design in the future. Arcologies for 50,000 people included in one place. Okay. So designing the habitats on other celestial bodies requires multidisciplinary approach. Both technical and technical expertise and understanding the behavior of human beings are required. It is necessary to understand development of population over time, evolving from young fit specialists towards society that includes children and elderly people. The design can be validated using adequate methodology using agent-based simulations. The presented methodology is only one of the steps in the correct risk assessment, so required on the early stage of the design. It can also be used in later stages of planning, of implementation, to develop emergency strategies. This all should serve increasing the design quality with focus on colony safety and well-being of occupants, so that ensuring that future development it becomes intact. In my opinion, organizations such as SFP and fire and evacuation modeling specialists should play a significant role in permanent human settlement in outer space. There are more materials on the webpage, nexusaurora.org, when you can contact our community. Thank you.
Thank you. Thank you. Great talk.
I just was reading. Okay.
Yeah, that's excellent. Any questions for the speaker? Yeah.
Thanks for your presentation. It's fantastic work. I was wondering, is it correct that people are supported to work slower in both higher or lower gravity scenarios?
I don't quite get it.
Yeah.
Do they move slower in higher or lower gravity scenarios?
Slower, slower, but except if you on the moon, when you start bounce. Do you remember Neil Armstrong? When he was bouncing, he was moving quite fast, but he was all alone. But when you are in the hole with many people, you start hitting each other and start squeezing, and then you walk on moon like that. This is the speed of the moon.
That's great. Anyone else? Oh, sure.
Do you have any plan to conduct experiment in Mars?
Conduct what?
Do you have any plan to conduct experiment in Mars?
In fact, it is already conducted by NASA, but there is no crowd formation because you cannot put a crowd in the plane. This is very difficult, and they just fly 20 seconds and go down. So try to make a crowd movement. This is something you will never fully discover unless you land on Mars and put there 50 people. It's not possible. It's just like that.
It's all
and
hypothetical.
when you are wrong, you're dead.
Right. Anyone else? One of the questions here says, I love the futuristic project, but please leave the flawed A-set, R-set concept on the Earth. We can do much better with risk-based approaches, and I believe your study would work with them well. So a comment from Wojciech Roginski. You can on his podcast, when you're the guest, you can have this conversation. Okay, anyone else? One here. Mohsin, I'm going to have you move to this side of the room. You can come sit next to me up in the front. Yeah.
How can you simulate or model hopping with Pathfinder?
You can't. You can't.
Okay.
You can't. You can't. All you can do is you enlarge you enlarge the collision response time. But there is a small thing in Pathfinder that we need to solve with guys that is not already solved, because bouncing, it's about the walls. It's not about the agents. So this you cannot bounce back to the people. Now it's only for the walls with a long collision response time.
Okay.
Or you can make one thing. You can make a drunk crowd and try to evacuate it. Because when you are drunk, you have a longer collision time response.
That's excellent. Thank you so much. Great talk.
Yeah,
Appreciate
thank
it.
you.